Hi, in this video I want to talk about my course on spice-based compact modeling for analog mixed signal and RF applications. I am Professor Abhishek Dikshit from Device and Wafer Level Characterization Lab, Integrated Electronic Circuits Group at Department of Electrical Engineering, Indian Institute of Technology, Delhi. That's in New Delhi, India. Here is a disclaimer that you should read. So why do we want to talk about compact modeling or spice-based compact models of for devices in the current scenario? This is a very interesting chart. So here is why we need to talk about electronic device technology in India, and in fact, globally, a lot of other countries already have a very well-established, this kind of a domain in their part of their economy, right? So India has a national policy on electronics that is approved by the government of India somewhere early 2019. And the idea is to boost electronics manufacturing and exports in ESDM sector. What this slide actually talks about is in India, this is an India specific slide. In India, the market share that India has is very disproportionate with respect to the consumption, with respect to the size of Indian market, right? So what it says is that a very large fraction of this kind of our economy is services based, right? So it has all kind of transport, energy, security, all kind of services, and this sector is very significant and it is growing further. And then you also see that dollar to INR conversion rates and prices of oil, these kind of segments actually largely determine what how much this grows or how much does this shrink. Okay, so this basically means that it is not really controlled by India that much. Below this sector, if you see, there is manufacturing industry, and India has manufacturing industry in automotive. Some industries are coming up in defense and medical and aerospace sectors. This sector has been for some time fairly low in Indian economy, and it has been declining. Now there is a lot of push from the government to actually boost this sector, right? Of course, there is a lot of competition that you have in this kind of sector from low cost regions of the world where manufacturing is available at a much lower price. But the good part here is that consumption in India is very high. So any boost that happens here, we are pretty much going to be able to consume it all of it ourselves, right? So that is very important that you have a ready market to supply to. Below this segment, you talk about electronic equipments. In the size, it is a much smaller market, but this is an inverted pyramid, so every sector is sort of relying on the sectors below it, right? So electronic equipment market India is kind of insignificant. It is an enabler, right? So the sector above electronics equipment, the manufacturing and services, is actually not really self-reliant, and if you don't have a electronics equipment segment, then you do have problems, right? Manufacturing industry, for instance, is very strongly tied to this kind of a sector, right? Again, consumption is very high, so that is positive in Indian terms. And then below this, the electronic components sector, where you talk about electronic ecosystem, which is more or less which has been missing for many tens of years. So this sector is pretty insignificant, and National Electronics Policy tries to boost this further. What is at the base of this pyramid, and very large proportion of Indian economy is in agriculture, mining, other raw materials. This sector is very disproportionate. It is very high in Indian economy. This is actually also called primary sector of economy, and it is very much affected by forces of the nature, the droughts, floods and things like that. Uh, this sector also has been declining, although it is very large. So a lot of people are moving away from agriculture and things like that. The trouble part is the money which is going out from this sector is not really getting into electronic component or electronic equipment, or even manufacturing sector. It is people resources which are moving away from the bottom of this pyramid are actually going to the top of the pyramid. So a typical example is a person based from a agricultural household, right? A family in a rural area. Uh, the family has very significant investment on the child, and he gets the education, grows up, moves to a big city, and becomes a part of services industry, right? So all your resources from agricultural family went directly into services industry. And once this guy starts earning in a city, right, in a metro city, calls the family, and in the end the one entire family which was doing agriculture has now moved along with its resources. They sold off their land and they are now all based in metros, right? uh, totally relying on the services sector. So that's the trouble part, right? And it's a disturbing trend, and we need to focus on electronic equipments and electronic components industry. So eventually our aim is to get a market share which is in proportion to the consumption. This is a must-have to sustain the Indian economy and make it very strong. Let's talk about the semiconductor product chain. I am trying to show, this is a slide borrowed from IBM advertisement. So here you see the whole range, right? So at the very top front end you have the infrastructure, very large data centers which further comprise of large systems. Blue gene is shown in this picture. And then of course you have packages, multi-chip modules and so on, which actually make these kind of systems. These systems make up this kind of a data center. If you go below, you see a integrated circuit, a chip here, right? And underneath the chip and below the chip you really get to the silicon technology level. So that's really the semiconductor product chain. There are companies which span across this chain, few companies. And there are companies which only specialize in a particular part or particular segment of this product chain. Both kind of companies are there, right? Okay. IBM of course is one of those companies. So based on that we can talk about who are the market players. So as I said in the previous slide, you have the product based companies like Apple, Nokia, Samsung, IBM, Sony. These companies make money by integrating components which are often ICs. Of course these are product based, so they are closest to the buyer, so their profit margins are also biggest. Then you have the component based companies such as Intel, IBM, STMicro, TI, ADI, RFMD and many more. These companies, they sell microprocessors, microcontrollers, digital signal processors, and many such things. This is a more competitive segment, so your profit margins are smaller, right? If you really talk about DRAM and flash, you will see that the profit margins are really small, right? And then you have the service based companies. Big name is TSMC. There's also Global Foundry, UMC, NXP, Tower Jazz. These companies, they sell technologies such as CMOS, RF CMOS, RF SOI, silicon germanium and so on. This is a specialty business, right? Very less competitive, not many people can do that. So profit margins are again much higher compared to a component based business, right? Okay. So to gain further perspective on the technologies and typical applications. You can see on this slide we have digital applications. Focus of your models is typically in the on state or off state of the devices, because the digital circuit so mostly has so it will look at the discrete information, microprocessors and many other chips, right? Similarly, RAM, DRAM, flash, FPGA, all kind of things, typically fall under these kind of digital applications. Then you have analog mixed signal, AMS-RF. Here, instead of just the on or off state of the devices, the focus is on continuous range of biases. So entire sweep of voltages is to be accurately modeled by the devices or device models. And then here you have things like power amplifier circuits, low noise amplifiers, band gap reference, RF switches, EST, and so forth. So if you see the analog part, analog mixed signal RF part, the RF focus, if you see in terms of what technologies are around, you're talking about 5G all the way up to almost 70 gigahertz frequency, right? Then 6G is coming, which is all the way up to 1.5 terahertz. Then you are having a lot of work ongoing in Wi-Fi 6 to 7 gigahertz. There is also some Li-Fi work started, which is typically going around for the autonomous vehicles and so on, right? So depending upon the frequency range of interest, right, the models require to be accurate up to different ranges of radio frequencies. And as the frequency increases, for instance, a lot of parasitics like capacitances and inductances, they become dominant, and they sort of dominate your circuit performance. So accurate modeling of passives becomes more and more difficult and important as you go to higher and higher frequencies. Another very important application coming up is in quantum computing area, and since the quantum computing qubits typically work down in cryogenic temperature ranges 10-20 millikelvin, the compact models have to be able to work down to these kind of temperature ranges. The control circuitry is supposed to work down to liquid helium temperature of around 4.2 degree Kelvin. So we traditionally have had models which really did not work at those low temperatures. Lowest we were looking at so far was like minus 150 degrees centigrade, right? So these 4 degree Kelvin and even below in millikelvins is a very low temperature. We have never explored what happens to compact models down to that temperature, and for that we need to, of course, freeze the devices to these temperatures and then do measurements, and based on that we have to extract their compact models. So this is, in a nutshell, it gives you a feel of what are all the challenges in the modeling area. So AMS Foundry, a lot of companies have gone fabless, they've gone fab light, right? They've reduced their fab capacity, and a lot of companies have stopped doing R&D beyond a certain CMOS node, right? So this is typically done to lower your operating costs to match up with the shrinking profit margins. There's a consolidation happening continuously in the market, and then you want to enhance your focus on innovation and product design, right? So once a company goes fabless or fab light, they still want to manufacture their products. Foundry is the place. Foundry is the unit that manufactures their products. You could talk about foundries which specialize in digital domain, such as TSMC. A lot of foundries which have a lot of work in analog domain, such as TowerJazz. And then you have companies which are looking at which are basically spanning across digital to analog technologies. IBM Microelectronics used to do that. Now it is part of Global Foundries. So that is one place where the entire spectrum of technology is available. So it is very important to actually understand that a company which has gone fabless and is trying to manufacture their products at a foundry, they have to be able to explain their design to the foundry. So they are going to design in a technology that is owned by the foundry. So how do you communicate, right, between the two units? That is very important. So if you see AMS Foundry process design kit, especially the enablement part, it sort of forms a bridge between the two worlds. On one side of this, you have the people in one company or company A who are looking at the product, who are looking at the system, who are looking at the circuit design. And on the other end of the bridge, you have the company B, which is where people are focusing on creating the technology, manufacturing the hardware, right? So when we talk about AMS PDK enablement, this serves as a bridge between the technology and circuit design, and hence it is one of the very important aspects of a foundry business. So a foundry may have very strong technology, but if their PDK enablement is not as good, the customer or the circuit design or the system design guys, they are not going to be able to utilize the foundry's capabilities. The capabilities of the technologies will be, not utilized to the fullest, right? So PDK enablement is very important, and it is also technology agnostic in a way. It existed 50 years ago, and it will exist for another 20, 30, 40 years, as long as you have a design that you want to manufacture on some piece of hardware. You will always need to simulate the design at the time of designing your chip, and you are eventually going to have to manufacture it in a specialized unit somewhere, right? The more consolidation happens in the market, the more the distance will grow between the two sides of the bridge, right? And the more the bridge will become important. So enablement is something which is very futuristic for coming 20-30 years. This is an example interaction between a customer who is a designer and a foundry. So foundry can communicate to them different kind of electrical parameters of interest for different kind of devices, such as transistors, resistors, capacitors, inductors, and many other such components that are going to be used in a on-chip design, right? And based on this, you create a model which of course gives these parameters as output. The circuit design people will actually utilize this model to simulate their design, and if the design works in using your model, the foundry model, then the design should work as well on the actual piece of hardware, and that's basically the commitment that the modeling people have. So most of the things I have said, this slide actually takes it to the next level, and it actually shows you what kind of ecosystem you need around your PDK enablement activities, right? And this is really a 360 slide, so you could start anywhere, but let us look at the customer driven list of devices which is of interest to the customer for design of a particular product, right? Then you talk about, so we go clockwise in this. So then you talk about technology development team, which will make sure that these devices they are able to manufacture. So technology development team sort of works on the process and make sure that all these devices are behaving well according to their specs on the same piece of silicon, right? One and single piece of silicon. Alongside this technology development team, you need to design test structures, right? And to design the test structures, you need to do something like a macro design, which is like a group of relevant test structures, right? So if these are, for instance, resistors, this is a group of similar resistors. So you can represent it as a resistor macro, for instance, right? So you have sort of your fab and manufacturing team here, right? Physical design team creates the layouts for these, right? Then you have the measurement people who are actually going to look at the device characterization aspects of this. So a lot of the guys who will put their test structures from the process side, from the compact modeling team side, all these people would want to measure these test structures, so they create the test plans for device characterizations which are measured in the measurement lab. So also it is equally important that other aspects, not just the intrinsic and standard performance of the device is analyzed. You also want to ensure that whatever you have designed will last the required age of the product, right? So reliability is very important. Then there is also design automation team, which is typically very active in creating the automation such as parametric cells, design environment, and they also help you with testing the kit, which will then have a complete model library for this new technology that is based on a customer request. And this will have all kinds of models. So there will be MOSFETs, there will be resistors, capacitors, inductors, all kind of models. And then the kit testing is all about making sure that all these different models they not only do what is expected out of them, but they also work as as components of a circuit, right? So in a circuit you have use for many such models. So then you are simulating circuits which are using multiple FETs, multiple resistors, capacitors, all at the same time within one circuit. So then you look at problems with any of your design automation issues, or even convergence of models, and these kind of issues. You basically look at the kit testing phase, and eventually your PDK is ready to be used by the customer, and they use it to design their circuits. And once they are satisfied with the circuit performance, then they basically give you a go ahead, and the foundry then manufactures the product. And so in this course, which is a 3-credit course, typically there are 2 lectures of 1.5 hour each per week. Typical evaluation breakup is also shown here. So students do up to 4 assignments which contain 40% weightage of the course. They do term papers, right? So term paper typically contains 20% weightage. Then there are 2 minor tests, each with 10% weightage, so this is 20 in total. And then there is a major test which is 20% again. A lot of times term papers and major tests, the weightage can be rebalanced depending on the situation. My contact is block 2, room 402D. My extension number is shown. And course outline includes briefly what we just discussed: introduction to AMS enablement and PDK elements, little expansion of that. Then we get into the basics of semiconductor devices, start talking about device modeling tools such as TCAD and SPICE. Then there's a detailed discussion on diode models, and then at the end of that there's a first assignment. Then the detailed discussion on resistor modeling. Then there is typically first minor test, then FEOL capacitor modeling, followed by MOS transistor modeling, which is the longest part of this course. And then there is second minor test, followed by some more advanced modeling exercise on variations, mismatch corners, and whatever else. And then there is a major test. The focus in this course is typically on industry standard models, so the models which were standardized by CMC. So the MOSFET models we cover, they typically include industry standard models. So we start with something like a BSIM 3v3, and then we often talk about BSIM SOI. Currently we are looking at BSIM bulk and BSIM CMG, so all kind of advanced models in terms of MOSFETs are discussed in this course. The other passive device models or other active device models such as diode models, these are, we try to talk about standard models. The biggest component of this course is actually the assignments which are done using Keysight IC cap compact model development and extraction tool. So there are live demos and lab sessions right, that students can remotely access and do the compact model extraction with given data. This course so far does not include any training or requirement for measurement or electrical characterization of devices. Whenever required, the data is actually provided to the students. All right, so that is all that is there for this lecture. Please do let me know if you have any further questions or comments on this. With that, I thank you for your attention. Take care. Bye bye.